Welcome to the distinguished lecture series of the Indian Mathematics Consortium. The aim here is to host virtual colloquia by some of the best researchers and expositors around the world. The speakers are carefully chosen by the scientific committee from among mathematicians who are not only distinguished researchers, but are also known for the quality of their exposition. The principal aim here is to make the talks as widely accessible as possible, especially to PhD students. With this in view, the format of most of the talks will be in two stages. First, there will be a pre-recorded talk by the speaker, which will be posted online. Interested audience can then view this at their leisure and communicate questions, if any, to the organizers. The second stage will be a live interactive session between the speaker and interested participants, and that will be held about 2 weeks after posting the online talk. The approximate duration of the talk will be about 45 minutes, and that of the interactive session will be about half an hour. The distinguished lecture series is co-hosted by IIT Bombay and ICTS Bangalore. Welcome. It is a real pleasure and honor to introduce Alex Lubotzky. Professor Lubotzky holds the Morris and Clara Vail Chair in Mathematics at the Einstein Institute of Mathematics at the Hebrew University of Jerusalem. Alex Lubotzky has made essential contributions to all aspects of group theory: geometric group theory, lattices and Lie groups, representation theory of discrete groups, as well as applications of group theory to combinatorics and computer science and error correcting codes. A theme that has recurred in his work very often is expander graphs. This topic will also appear in his talk today. We will see in his talk a demonstration of the organic unity of mathematics that is a hallmark of Alex's work, something that makes it both exciting and inspiring. Some of the ingredients that will appear, just to give you a sneak preview: sofic groups, then symmetric groups, hyperlinear groups, unitary groups, expanders, all of them gelled into an organic whole. I'm really looking forward to hearing it. Thank you very much.
Good morning or good afternoon in India. My name is Alex Lubotzky. I'm talking to you from Jerusalem, from Israel. And I would like, and thank you very much for the invitation to give this talk. And I'm actually quite excited about this opportunity and also about the spatial format of this talk. I will present now the talk with no audience, but I understand that we'll meet in few weeks and then we can discuss the talk. I will not give it again, but we can discuss it and talk a little bit more, and it will be also an opportunity to expand about various things that I will not have a chance to talk about today. So the talk about is stability, non-approximate groups, and high-dimensional expanders. No background is assumed. I will try to explain everything. Let's recall that a group gamma is called residually finite if for every G in gamma, every element in gamma which is not the identity, there exists an homomorphism from gamma to some finite group F such that phi of G is not the identity. Namely, a group is residually finite if we can separate the points of gamma by homomorphisms to finite groups. Equivalently, it means that the intersection of all the subgroups of finite index is trivial. Equivalently, it means that the intersection of all the normal subgroups of finite index is trivial. And equivalently, and maybe more relevant for us, is that for every G, not the identity in gamma, there exists an homomorphism to the symmetric group on n letters, but n is some number. some finite number depending on G, such that phi of G is not 1. This is, of course, follows from the definition because we know by Cayley theorem that every finite group can be embedded into the symmetric group, so we can just think of every homomorphism to a finite group as a homomorphism to a symmetric group. But in a minute, you will understand why I prefer this formalism. Anyway, many groups you meet in the street are residually finite, every finitely generated, I stress here, finitely generated linear group is residually finite. The automorphism group of a free group is residually finite. The mapping class group is residually finite or not. But there are many groups, including finitely generated groups, which are not residually finite. For example, there exist infinite simple groups, even finitely generated infinite simple groups, and these are not residually finite. Now, this is an old subject in group theory, not only in group theory, but also in other objects, in algebra, in other areas of mathematics. Like you want to understand a complicated object by kind of separating or look at it through a microscope or a telescope, depends how you want to think about it, which see small parts of it. And by this, you can deduce something about the complicated object. And residually finite is like that. If the group can be seen from its finite quotient, we can deduce various properties on gamma. For example, if gamma is a finitely generated residually finite group, it's known that the so-called word problem is solvable in that group. And you can deduce various things about such groups. But this is not my topic today. My topic today is an extension of this notion for a more general class of group called sofic. So let's now see what is the definition of a sofic group. Gamma is sofic if there exist maps phi n from gamma to sim n. I'm sorry, this is not the same n, or maybe it can be the same n, but it's from the symmetric group phi n to some finite to the symmetric groups. But I'm stressing these are maps. Upstairs it was homomorphisms. Now I'm talking about maps which are not necessarily homomorphisms. They are just maps satisfying the following property. For every GH in gamma, the limit when n goes to infinity of the distance between phi n GH and phi n G times phi n H is equal to 0. So in a sense, think about it, that these are maps which are eventually, which are kind of converges to look like homomorphisms with respect to this distance. What is the distance? There is a natural distance function on the symmetric group, which is called the normalized Hamming distance, which is defined to be as dn of tau sigma, like the distance between two permutation, is the number of I in the set 1 up to n for which, it's missing here, it should be sigma of n is not equal to tau of, there are too many mistakes here, I'm sorry, too many typos. Sigma of I is not equal to tau of I. It's the number of points for which sigma and tau are not equal to each other. This is a number between 1 to n, between 0 to n, maybe they are equal on everything, and then this is the same permutation. And you normalize it by dividing it by m. So this is called the normalized Hamming distance. So for every G and H, eventually they almost behave like homomorphism. But of course, you can always find such map. For example, send everything to the identity. We want to separate the points, And the meaning of separating the point is that for every, that's the second condition, for every G in gamma, which is not the identity, the lim sup, or you can actually say the lim inf, maybe it would be even better because, but it doesn't really matter. One can, if you have with lim sup, you can arrange a class with a lim inf. Anyway, dn of phi n of G, the distance between phi n of G and the identity is some number which might be dependent G but bigger than 0. So it's kind of, it's bounded away from the identity. You don't want to send all the elements to the identity or to something very close to the identity. Then you can satisfy condition 1 in a trivial way. We don't want that. We don't really, we say that we can separate the points, but by homomorphism in a non-trivial, by almost homomorphism. So usually this is say if residually finite is a group which the points can be separated by homomorphism to the symmetric group. Group is sofic if the points can be separated by almost homomorphism to the symmetric group. So it's clear that every residually finite is sofic, but there are other examples. For example, every amenable group is sofic. Now, if you don't know what is an amenable group, either go to Wikipedia or you can ask me when we will meet, and it will be a very good exercise to check why amenable group is sofic. If you look at the Follner set, you can see that every element of the group pushes the Follner set, it acts on them like almost homomorphisms, and it satisfies these two properties, and we can discuss this further when we'll meet if you cannot see this. So we see that sofic include residually finite group, include amenable group, and it's richer than both because there are amenable groups which are not residually finite, there are residually finite which are not amenable, for example, the free group, and there are groups which are neither amenable nor residually finite, but they are sofic. In fact, In fact, a major open problem in the last 30 years due to Gromov and Benji Weiss ask, are there non-sofic groups? So far, we don't know a single group which is not sofic. We believe now that there are non-sofic groups, but we don't know. That's a major open problem, maybe one of the most outstanding open problem in group theory is, are there non-sofic groups? Why this is so important? Because now it's even more important than when it was asked, because there are a good number of theorems which start like that. If gamma is sofic, then blah, 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 then Kaplansky conjecture about something is true for that group. So you see, there was a conjecture of Kaplansky about the zero divisors in the group algebra. It doesn't matter. I don't want to elaborate on that. What my point is that there was a conjecture that something happened for every group. It was proved for sofic group. So now if every group is sofic, then it's true for every group. But we don't, as I said, I think most experts do not believe that all groups are sofic. We don't know to answer that, and as we do quite a lot of mathematics, if we don't know to answer, we generalize, but we will see that the generalizations are interesting and also important. So let's talk about a more general situation. Let's Goetic G be a family of groups Gn with matrix Dn on them, bi-invariant matrix on the groups, and we say that gamma is G approximated if there exists maps, not homomorphisms, I stress, maps from phi n from gamma to gn such that, one, they are asymptotic homomorphism. Just before, this is the definition of asymptotic homomorphism, namely, for every g and h, the lim of the distance between phi n of gh and phi n g, phi n h is going to 0. They are almost the same eventually. And also they separating the point of gamma, which again is as we defined before, condition 2, that for every g, the lim of the dn is bounded away from 0, namely it's not very close to the identity. It's not too close to the identity. And what are the interesting examples that we will talk about today? There are a few more, but these are the main examples that are of interest to study of such families. So let me give you a number of examples like that. So the first example is the example we already discussed. Gn are the symmetric groups, and Dn are the normalized Hamming distance. And now, if gamma is G approximated with respect to this family, we said that we call this gamma sofic. Now, I'm going to give you a few more examples. In all of them, we will take the same groups, but with different matrix. And I want to stress that that the notion here depends very much not only on the group, but for every group, it's really important which matrix we work with. So the groups now will always be the unitary group, the n by n matrix, the unitary matrices over the complex number. The matrix we will take will always be defined using some norm. The norm will be different. Now I will present you several norms. Each one of these norms will define the metric on the n by n matrices, and therefore a matrix on the unitary group. And these will be the matrix that we will work with. Let me just set up a notation that we'll use all the time. If A is an n by n complex matrix, then it's easy to see that A star is simply the adjoint. A star A is a normal matrix. We know from elementary linear algebra that every normal matrix can be diagonalized. Moreover, the eigenvalues are real. And in this case, because it's A star A, it's a little exercise to see that they are not just real, but they are always non-negative. Therefore, we can take square root of this matrix in a kind of a clear way. We take the non-negative roots of these eigenvalues, and we can talk about the absolute value of A, which is a matrix. Don't get confused. It's a matrix. Don't get confused here, which is the square root of A star A. And now we are going to define the following families. Example number 2, Gn is the unitary group. Dn, the matrix will be defined using, it always be defined like that. The matrix, the distance between G and H is the norm of G minus H. Then now the norm will be the Hilbert-Schmidt norm. What is the Hilbert-Schmidt norm? This is you take the trace of the absolute value of A square. The absolute value of A is simply A star A. You take the trace of it. So this is basically taking the sum of the squares of the eigenvalues, normalize it, dividing by 1 over n, and then takes square root of n. Now, if you take this family of groups, what does it mean to be G approximated? We know, I mean, there was a definition. It turns out that this is not a new definition. People were interested in these type of groups and with the Hilbert-Schmidt matrix. And groups which are G-approximated are called in the literature hyperlinear groups. To be honest, hyperlinear groups is not such a good name because it looks like hyperlinear group is more than linear. It's less than linear. It's a special case of linear, but actually it's more general than linear. Every linear group is hyperlinear and not vice versa. In fact, every residually finite group is hyperlinear, but not vice versa. Now, sometimes people call it Cohn's embeddable groups. Why? Because Alan Cohn's studied this. I will in his famous Cohn's embeddable conjecture, which was recently been disputed for algebras, which is an interesting and related topic. But maybe when we'll meet, I can elaborate a little bit. It's a fascinating connection between this area and quantum computation, but I will not discuss it today. Anyway, some people call it Cohn's embeddable groups. One can prove that every sofic group is hyperlinear, and of course we don't know the converse because maybe every group is sofic, and it's another major open problem due to Alan Cohn's whether every group is hyperlinear. Let me take other examples. Example number 3 will be again the same group, unitary group. This time we'll take the Frobenius norm. What is the Frobenius norm? It's simply exactly the same, the trace of a square, the absolute of a square, and then square root of the trace, but without normalizing. That's all. You will be surprised, or maybe not surprised, to see that it's a completely different problem now. If a group is approximated with respect to the Hilbert-Schmidt norm or with respect to the Frobenius norm, you cannot deduce from one to another. Think about it for a second. You see, the Frobenius norm is always greater or equal than the Hilbert-Schmidt norm, which means that if you have a set of almost homomorphism with respect to Frobenius, then they are of course almost homomorphism with respect to the Hilbert-Schmidt. But maybe they are separating with respect to the Frobenius and not separating with respect to the Hilbert-Schmidt because the Hilbert-Schmidt going to zero faster than Frobenius. Think about it, stop the recording and think about it. You'll see that these are completely two problems. You may ask yourself which one is more difficult, like to prove that something is Frobenius approximated or Hilbert-Schmidt approximated. At this point is not clear. Maybe toward the end of the talk, we'll get some insight to this problem. We can generalize this Frobenius by doing, instead of L2, something like LP. This is usually called the Schachten P norm. We take, again, P, any number between 1 and infinity, and we define the P norm of A to be the absolute value of A to the P. Then we take trace of it, and then we take 1 over P. This is like taking the LP norm of the eigenvalues. P equal 2, by the way, is exactly the previous example. But here we have uncountably many examples of families. And again, if you think about it for a second, there is no connection between the problem if you are P approximated or Q approximated. If you know the group is a P approximated, you cannot deduce that it's Q approximated for some other Q. The last example for today is the operator norm. Again, we take the operator norm as a norm on the matrices. So operator norm is simply we go over the norm of AV, where V run over all the vectors of norm 1. And we ask whether, so again, we get the unitary group with the operator norm, defining a metric on them. And we ask whether every group is approximated by the unitary group with the operator norm. This is also a classical problem due to Kirchberg. In the literature, groups which are operator approximated are called MF, and it's a major open problem whether every group is MF. The good news is that we have answer to some of these problems. So in some sense, the breakthrough came in the work with Marcus de Chiffre and Lev Glebsky and Andreas Thom, where we were able to prove that there exists a finitely presented non-Frobenious approximated groups. There exist such groups which are not. For the first time in this type of problems, we were able to show a negative answer that there is a group which is not approximated. Shortly after that, in a joint work with Izhar Oppenheim, we managed to generalize it and even to say that there exists one finitely presented group which is not p-approximated for any p greater than 1, less than infinity. Solving almost all the problems I presented before, solving, if you want, uncountably many problems, and leaving out only 4 open problems. Sofic, whether you remembered example number 1, hyperlinear, example number 2, MF, example number 5, and the case of p equal 1. So this is great. Unfortunately for us, these 3, the first 3 are the most important one. They are the classical problems in the literature that everyone was thinking about. The others, they were mentioned in the problem as a generalization, but somehow they are not of the same importance. But you may ask why those are more difficult than the others. I think part of that work, the importance of our work, is that suddenly we understand something which was not at all clear to us and probably also to other people, that there is a difference between the problems. Now we see that there is some difference, and I will see a little bit the difficulties. Maybe I will be able to elaborate it when we will meet in a few weeks and discuss it further. Let me, in the rest of the talk, give you a kind of a sketch of the proof. And again, we will be able to say more when we'll meet, but now I will keep. For the sketch of the proof, I must give you 5 minutes crash course on another topic, which is called group theoretical stability. What does it mean? Stability is an issue in all of branches of mathematics. You know, you have a differential equations, and say you have you find an almost solution. You know, you find a solution which almost satisfies it. Or you have a polynomial, not even differential equation. You find a solution to it. Is it clear? Usually it's not clear. Sometimes even not true that the almost solution is nearby an honest solution, a true solution. We can ask it such a question also in the context of group theory. So let G, Gothic G, be a family as before. Groups Gn, each one is a node with a matrix Dn, and gamma is a group, say a finitely generated group. Then gamma is G stable if whenever we have such class of maps, gamma from gamma to Gn, which are asymptotic homomorphism. You remember, these are maps which are not really homomorphism, but only almost homomorphism. Now, we say that gamma is stable with respect to G if whenever you have something like that, they are just a small deformation of honest homomorphism. Namely, there exists true homomorphism, psi n from gamma to Gn, such that for every G in gamma, the distance between psi n of G and phi n of G goes to 0. again, I'm not going to elaborate here, but there is a beautiful connection. If some of you will want to hear, ask me when we'll meet, with a subject called testability in computer science. Property testing or testability is an extremely important subject in modern computer science. Sometimes goes either the name PCP, probable checkable proof, which is maybe the PCP theorem is maybe the deepest theorem in theoretical computer science. And there is a connection to that. We can think about such stability as a spatial case of testability of some equations. There is an interesting analogy to Galois theory. You can replace equations by groups and then study the solvability instead of the solvability, which is the issue in Galois group, the testability of the equations by the testability of the group. I will not stop to explain it now, but we can elaborate it when we meet. Now, the starting point of the proof of the theorem I described today really goes back to the work of Glebsky and Riviera, which was with the following very easy proposition, which says the following. Assume gamma is finitely generated group, which is G, let G be as above, and like a family with matrix, and gamma finitely generated group. If gamma is G approximated as well as G stable, then it must be residually finite. Why? That's every lecture should contain a proof. Let me prove it. It's very easy. Assume gamma is G approximated, then this means that there exists a asymptotic homomorphism from phi n to gn, which are separating the points, right? But if at the same time gamma is also G stable, this implies that I can move these maps just a little bit to get homomorphisms from gamma to Gn, which are also separating. Think about it. You see that if you just move it a little bit, and one is separating, the other one is also separating. So I have a separating homomorphism from gamma to Gn. So gamma can be separated by homomorphisms. In the first example is homomorphism to Sn. In the other examples is homomorphism to the unitary group. When you take homomorphism to the unitary group, the image is finitely generated linear groups, right? The phi n of gamma in this case are finitely generated linear group because they are the images of gamma. But you remember from the first slides, right? This is like in people say on shows by Brecht that if you see a pistol on the desk in the first show, it will shoot in the last one. So you remember in the first slide that linear groups are residually finite. So we can separate the points of gamma by homomorphism to finitely generated linear groups. Each one of them is residually finite. So each one of them can be separated by homomorphism to finite groups, and therefore gamma can be separated by homomorphism to finite groups, and therefore it is residually finite. So this is very suggestive because this means that this proposition, it's just a way to prove a theorem like that. Why? Because if gamma is finitely generated and G stable and not residually finite, then it is not G approximated, right? This is just reformulating this proposition. If gamma is finitely generated, G stable and not residually finite, then it is not G approximated. So we have now a method to prove non-G approximated, to find a non-sofic group, to find an non-hyperlinear group, to find non-G approximated. Well, this is easier to say than to do. Why? Because it's very difficult to prove that something is G stable. Again, I will not elaborate of it now. Till like 2-3 years ago, there were hardly any method. People prove for various groups that they are stable, but usually it was groups like a billion groups. So of course, a billion groups are sofic, so it won't help you, but even to prove that a billion groups are stable is a non-trivial theorem. Think of it as an exercise. To prove that a billion group is sofic, a billion group is stable with respect, say, to unitary matrices, you have to say that if you take two unitary matrices which almost commute in one of these matrices, then nearby you can find two matrices which honestly commute. This is a non-trivial result, and it's not always true. Depend on the matrix. That's fascinating subject, which I will not go to it now. It's actually this case of commuting originated in mathematical physics, because of the Heisenberg uncertainty principle. People were interested in problems like that. If you take two matrices to Hermitian matrices, which almost commute, are there nearby commuting matrices? There are dozens of papers about this type of questions. Again, but we will continue. As I said, we don't have that many methods to prove stability, but suddenly there are few general methods. And one of them, in some sense, this was the main breakthrough in the work with Schifre, Glebsky, and Tom, that suddenly we have a criterion, not if and only if criterion, we have a sufficient condition for a group to be stable. And this is the following. Assume gamma is a finitely generated group, and assume H2, the cohomology group of gamma with coefficients in V is 0 for every unitary representation of gamma on any Hilbert space V, then gamma is stable with respect to the unitary group and the Frobenius norm, the Frobenius metric. You may be surprised by that, because what this H2 has to do? What the cohomology, how the cohomology suddenly come into the game here? What this has to do with the whole subject here? Well, I want to explain it now. Again, if you will ask me when we'll meet, I will say more about that. Maybe I'll say a few words today if I'll have time. Depends. I see that the lecture is starting to be a little bit longer than planned. Anyway, suddenly we have a criterion that H2 gamma V is equal to 0 for every unitary representation. Now, for some of you, this may remain something. There is something like that about H1. If H1 gamma V is equal to 0 for every unitary representation of gamma on any Hilbert space, this is exactly known to be equivalent to Kashdam property T for gamma. Kashdam property T is a very important property for Lie groups or for finitely generated groups studied by Kashdam. Again, I would recommend you to go and look at various sources, a little bit about that, even though we don't really need it for our topic, but it's, and suddenly we have, instead of H1, we have H2. Okay, let's continue our story. Where can we find groups like that? Groups like that can be found by Garland theory. Now we are starting a third lecture on something else. Let G be the group a simple p-adic Lie group. What does it mean? We look at the field of p-adic numbers, right? This is a locally compact group, just a nice, this is a locally compact field, just like the real number. I can talk about groups over p-adic numbers, or Lie groups over p-adic number. For example, SLN QP, this is a p-adic Lie group. SPN, the symplectic group, 2G over QP is such a group. To every such a simple group, Brua and Titz associated what is now they call the Brua-Titz building associated with G, whose dimension is equal to the QP rank of G. Like, for example, the QP rank of SLN of QP is n-1. The QP rank of SP2G is G. So there is some building. What is this building? This is an infinite contractible simplicial complex on which gamma acts. Let gamma be a co-compact lattice. What does it mean, a co-compact lattice? It means that it's a discrete subgroup in G, which is co-compact. Now, G acts essentially transitive on the building. So this building, this infinite simplicial complex, when you divide it by gamma, you get something which is compact because gamma is co-compact in G. But at the same time, this is a simplicial complex, so it's discrete and compact, and therefore it's finite. This is a finite simplicial complex. You can get very interesting simplicial complex like that, and in my title I mentioned I-dimensional expanders hinting toward these simplicial complexes, which are in some sense, not in some sense, they are I-dimensional expanders. Again, this is something that I will not elaborate now, but when we meet, I can say a few words about it. Now, Garland proved, as a response to a conjecture of Serre, and this was extended by Bolman and Lubotzky, that if P, now this is the P here, the P is the P of the p-adic, is much larger than the rank, than R, then HI gamma V is equal 0 for every unitary representation on any Hilbert space V, and every I greater or equal 1 strictly less than R. Okay, this is the theorem. Let's not talk about its proof now. It's a classical theorem by now. But this theorem gives us a big source of examples of groups satisfying what we needed, right? We needed group which satisfied H2 gamma V is equal 0 for every unitary representation on every group. Here we get HI for every I between 1 and R. So if we take R greater or equal 3, there are plenty of Lie groups like that. We will get many gammas with H2, and therefore they are stable. Wonderful. But they are all lattices and p-adic Lie groups. They are all linear, so they are all residually finite. And you remember our goal was to get groups which are finitely generated. That's fine. All these co-compact lattices are finitely generated. G stable, this is fine, but they are all residually finite. So what we gain nothing so far, right? In our goal to get a non-approximated groups. Well, there is a way to continue. Okay, these are not the groups which solve the problem for us because they are all linear and therefore residually finite. But in 1973, Delin showed that for some non-uniform arithmetic lattices gamma in real Lie group, in the symplectic group 2G over R, you can find finite central extension. We start with such gamma. We have a finite, we have gamma tilde, which is mapped onto gamma with a finite kernel, which is even central in gamma. And he constructed such examples which are not residually finite. Well, to be honest, I don't know why he did it. But later, Raghunathan extended this for some co-compact lattices, uniform lattices, not just like the original examples. Later on, these works became famous by the work of Toledo, because Toledo used them to find to settle an old problem that pi1, whether pi1 of a projective variety is always residually finite or not, and he used them to get counterexample of some projective varieties of non-residually finite. When I was recently in India, I asked Raghunathan why he was interested in that. He gave me some explanation, but I'm not sure I can repeat it. You may want to ask Raghunathan, who is in India and is one of my mathematical heroes. He's a great mathematician which influenced my work a lot, and also is a wonderful, wonderful person. And I'm sure he can explain this material better than me. Anyway, I have to admit that I have a difficulty to understand the proof of Deligne, and not only because it was written in French, but fortunately, and I want to mention it just to show that sometimes it's very helpful, Dave Whit-Morris at some point gave a seminar talk on Deligne work and wrote some notes and in his own language and put them on the on the internet, and I found them, and then I could understand his work, and therefore we could do exactly the same over the p-adic numbers. Namely, we look at the p-adic Lie group, this SP2GQP, gamma arithmetic co-compact lattice. We imitate the work of Deligne by getting a central extension of such gamma, which a finite kernel, and it's not residually finite. Now, it's easy to use some standard, it's called spectral method in cohomology, to deduce that if gamma satisfies the H1 and H2 for gamma are always zero, that's we get from Garland, right? And this is just a small finite extension of it, that the same results hold for gamma tilde. So gamma tilde also satisfies that H2 of it is always zero, and therefore, and at the same time is not residually finite. And therefore we got that gamma tilde is not Frobenius approximated. As I said, shortly after that, Izhar Oppenheim and I managed to extend it to all the p-norms, basically by extending the Garland theory to Banach spaces rather than only Hilbert spaces. So when we'll meet, if you will be interested, I can elaborate on that. And I think I will finish now because my time is over, but when we meet, I can show you 2 more slides, which giving some explanation about cohomology. Those of you who are not familiar with cohomology, I would suggest them to look at the very basic, just like what is H1, what is H2, and especially to understand that vanishing of H2 is related to various lifting problem with abelian kernels. That will be what we will, the way we use the cohomology. Okay, that's all for now. Thank you very much. And we will meet in few weeks to discuss this further. Thank you very much.